Hi friends, this is the lecture where I would like to introduce how integration should be understood and handled. The basic point is we would like to learn the integration of multivariable functions, in particular the double and triple integrations. But much before that, one has to get a quick review about single variable integrations or the integration of single variable functions. Now, the most basic principle behind integral calculus is the so-called fundamental theorem of calculus. It all begins from this point. The fundamental theorem of calculus is that theorem that links the concepts of differentiating a function with the concept of integrating a function. They are two operations which are inverses of each other. That is why we many times call integration as anti-differentiation. And this can be explained somewhat like this. Now, f is the function that we would like to integrate. And suppose one can find a function g such that the derivative of g is equal to f. Conversely, we can say that the integral of f of x is equal to g of x, with of course a constant being added. Now, this is the genesis of the concept of integration, coming through the antiderivative concept, which comes through the so-called fundamental theorem of calculus. What are indefinite integrals? Indefinite integrals are those integrals where you don't subject the integration to any limits. So this should graphically explain that differentiation and integration are inverse processes of each other. Now, as already introduced, the definite integral is that integral which comes with limits. Many times, whenever we would like to apply integration to physical problems, we will have to restrict the integration to a certain domain. This domain, of course, can be a finite domain, sometimes infinite domain. And obviously, two very important concepts arise: that the integration of a function in a finite range, which are called proper definite integrals, and sometimes we will have to integrate over an infinite range, and those are called the improper integrals. So if you look for a working formula for the definite integral, suppose the antiderivative of f of x is g of x, then the job is very simple. You integrate f of x and then you get a function g of x, then subject this g of x to the limits a and b. A is called the lower limit of integration and b is called the upper limit of integration. So evaluate the function g at the upper limit b, and then from that you subtract the value of the function g at the point a. So this can be the sort of working rule, provided you are able to get that g of x through an integration process. In very simple situations, this g of x is achievable, but there are many situations where the g of x cannot be determined. Then what do we do at that point? So these are the issues that we are going to address in the future lectures. Now, you can never learn mathematics, or for that matter any abstract science, without knowing where they actually occur in the physical scenarios. One of the very famous or the simplest things that we can visualize about the definite integral is the area under a curve. Now you can see that we are integrating, or we are trying to find the area of a curve that you can see as a continuous curve running from the extreme left to extreme right within two vertical bars that you can see. And this particular curve sometimes goes below the x-axis, sometimes goes above the x-axis, of course, alternatively. So wherever the curve is seen above the x-axis, that region is given a positive sign. And wherever you can see the curve going below the x-axis, which are shown as red areas, are given negative signs. On the whole, the output of this particular integration will be positive because finally area can never be a non-negative quantity. So you have to just keep that so-called signed convention. Wherever the curve goes above the x-axis, give a positive sign to the area. Wherever the curve goes below the x-axis, give a negative sign to the area. This is one area, particular situation where definite integrals are encountered. We can call this one of the simplest of the cases. Then there are something known as probability integrals. Now this is extremely useful wherever you find uncertainty in measurements of physical quantities. These things normally happen in signal processing and other areas, or wherever we are trying to study market research problems that we're not damn sure about whether we will be able to definitely predict a certain characteristic about a process. So this is where the theory of probability comes, and a probability integral is that integral which arises whenever we know the equation of the probability curve. In the case of continuous functions, we call them probability densities, and we integrate this probability density curve between two assigned limits. But the theory is very, very clear. If you integrate over the entire range, the area should end up to 1. Otherwise, you can take slices of this region, and then you can get probabilities that are that will finally lie between 0 and 1. We'll come to those issues when we have lectures on probability theory, but this is one of the areas where definite integrals are used. As discussed earlier, this is a classical case where we have two graphics where we are trying to find the area under a curve. In the first case, we are trying to find the area under the curve above the x-axis between two limits a and b. Whereas in the second one, which is a little bit more complex to initially understand, is to find the area between two curves y is equal to f of x and y is equal to g of x between the range a and b. So we will deal with these things, but I'm just first trying to explain to you the context in which definite integrals are encountered. Now this is one area of physics that is a very familiar diagram, but not exactly the complexity that we are looking for. But this is the so-called velocity time graph. And if you integrate the velocity function, you get the total displacement. And this is one area where definite integrals are seen. Of course, what you're seeing in this graphic is the velocity curve as a polygon, but calculus is at its best when that velocity curve is a smooth curve. So integration arises even in physics. Then this is an example from economics where we talk about the total investment of the stock, or to derive the total cost function or the total revenue function or total production function from the marginal functions. So even though these are technical terms at the moment, but if you have the so-called investment demand curve, then you can integrate it within specified limits, and then you can derive the so-called total cost or revenue or production. So even an area like economics cannot stay away from integration. So calculus is all pervasive. And this is one of the highest level examples that we can talk about and very rarely seen in books, textbooks. This is a problem from clinical biology where we are talking about the pumping rate of the heart. Now you can see this is the diagram of a graphic of the heart with all the important um, veins and arteries and the chambers of the heart through which blood flows. And one has to understand these very important things in order to talk about an application like this. How much is the heart pumping? At what rate is the blood being pumped by the heart? Okay, so let me not assume any much domain knowledge from you people, but you can see on the right hand side that there is a formula that gives a cardiac output as F is equal to A by the integral of C of t dt from 0 to t. F is the flow rate, that's what we are trying to calculate. And you know that typically you first inject a dye with a certain concentration. Of course, you must know the concentration function C of t. And then between time 0 to t, you integrate. And then this particular formula gives us the heart pumping rate. This is how clinical biologists or medical doctors handle. But I would like to tell you that they are all novices in mathematics. So they just depend upon some tables and then based on that you make judgments. But we are the people who provide all that knowledge to anyone. And what more integration can do? There are plenty of applications and the list is not exhaustive. I just gave you some samples just to motivate you that integration is practically a very important tool that you cannot ignore. So what do we do after this? So this is what we'll have to await. What I would like to do is, I would like to share in my next lecture some problems. This is for students who are beginning integration for the first time, and they can see through my examples that integration after all is not a forbidden area and one can learn very, very easily. So let us meet again the next time. Thank you.